Let me start recording. Okay, so let's get started with the second lecture. So this lecture is called Connecting Dots, AI Cookbook for Nuclear Physics. So it's actually a kind of a complementary part to what you have learned from yesterday. So this is a lecture I really want to give since a long time ago. So why do I want to give this lecture? Because I feel like there is actually a pretty large gap between AI ML community and the nuclear physics community. So the AI ML is a very, very huge field. So I attended this AI ML conferences a few years ago. So there are like 5,000 participants for the conference. So everyone is like staying in this huge like warehouse to look at posters and listen to talks. So this is so it's much, much larger than a conference that we really go to in nuclear physics like DNP, for example. So having those many researchers means they also have many, many different research directions, and they develop a lot of different models. They do a lot of very, very fancy things within the AI ML community. But from the nuclear physics, from the physics side, we prefer to kind of approach the problem in the physics way, like more like the first principle way. But there is also an AI ML model that can actually help you do the same thing or even do these kind of things better. But the only thing that we do not know that this kind of model exists. So this is exactly the purpose. Why do I want to make this lecture? Because I want to get you guys exposed to these different fields in AI ML, so to know that it actually exists and it can be used to solve the actual problem you will encounter in your nuclear physics research. What happened to the slide? Thanks. So in the lecture yesterday, I hope you didn't forget about it yet. So we set up the foundation to understand some of the more advanced machine learning models. So there are a lot of technical details in lecture one, but it's not going to be in this lecture because there is only a fixed amount of information I can convey to you guys in this very short 1.5 hour lecture. So I have to sacrifice some of the depth in order to increase the width to really tell you what is, to really give you a very broad overview about what's happening in the AI ML community. So that's why the main objective of this course is going to be, as I said, suggested in the title, is going to be connecting dots between AI ML, the AI ML field, and the nuclear physics field. So after finish this lecture, I want you to walk out with this kind of sense. It's like, I don't know all the details about those fancy machine learning models, but I know there exists an AI ML method, a recipe that could solve the actual problem I'm facing in nuclear physics. So that's why I'm saying this is a cookbook. It's not directly giving you a dish you can eat, a cuisine you can eat, but it gives you a recipe and you have to cook the dish yourself. So go to search on Google, try to find some code and try to start getting your hands dirty and build those models. I think this is kind of the take-home message I would like you guys to have after you finish this lecture. So for this lecture, I also designed this two kind of blocks. So there's no code, no equation, no theory. Just one block is nuclear physics. It's a question I received from many of the nuclear physics students who reach out to me and ask me, "Hey, Obo, I have this kind of question. I just have this kind of challenges in my experiments. What kind of AI model should I use to solve it?" So those are the questions I kind of logged down in this lecture slide. So I have 6 of them. I use those questions to kind of guide the flow of this lecture slides. And also the second block is AI ML, which is the research directions in the AI and machine learning community that could help us actually solve those nuclear physics challenges that was raised from students. So I'm going to try to go through each of these questions. And at the end of every question, I will leave some time for you to ask questions if there are some confusion about the concept. Okay, so let's get started with a very quick review about what I told you yesterday. So we had yesterday we had a very detailed kind of a description about how to build a neural network, starting from data processing all the way to evaluation. So in data pre-processing, we discussed the Marana demonstrator datasets from the high purity germanium detector. We discussed about how we can pre-process our data to transform it, and also how we can build this data loader. So we also discussed this feature extraction network. Remember, it converts our input waveform, which has a size of 1000, into a 32-dimensional, low-dimensional vector. And we discussed how to create this in PyTorch. And then we discussed about our task module, which was unfortunately blocked by my Zoom. So it contains a task layer and a loss function. And we discussed how to modify our task module to do different kind of tasks. using a machine learning model. For example, we can do classification task, we can do regression task, or we can do some other task. And then we talk about how we can train our machine learning model using the so-called, let me try to see if I can hide this. Hide floating media control. Okay, great. So using the stochastic gradient descent algorithm and the backpropagation. And lastly, I discuss about what happened. I discussed about how we can evaluate our model using the ROC analysis and the area on the curve. So given the information we conveyed yesterday, I'm gonna kind of summarize the machine learning model, the structure of the machine learning model into this kind of flowchart. So we have some raw data. We did some data pre-processing. Remember, we are windowing our data, we are normalizing it, we are doing standard scalar, and we convert it into the input data we actually want to feed into our neural network. So that's the 1,000 dimensional waveform that we actually want to feed into our neural network. And then we build a feature extraction or a feature extraction network, which convert this 1,000 dimensional data into a low dimensional representation. So a low dimensional vector, that vector is 32 dimension. Remember, we have 3-4 layers that's take an input of 1,000 and output a 32 dimensional vector. I call this vector, I give it a name. I call it a representation of my input events. And then I feed this representation into my task module, which contains the task layer plus the loss function to actually do some kind of task, either a classification task or regression task, and that gives the outputs of my neural network model. So today I'm gonna go through, I'm gonna talk about another branch, which I outlined on the bottom, which is we do feature engineering over the raw data to convert it into a tabular data and use some non-neural network classical machine learning model to produce output. So you don't need to understand what this is at this point because I'm going to talk about it right away. So this is mainly kind of the overall kind of framework we are going to fit our content into. So you will see I'm going to talk about, hey, for this part, what we can do, for this part, what we can do, for this part, what we can do. That's how the lecture is going to flow for today, basically. So first, let me give a very quick overview about some of the terms you may be hearing about within the AI community. So we talk about artificial intelligence, machine learning, data science, deep learning. So what are those words actually means? How are they different from each other? So artificial intelligence or AI is a very, very big field. So for example, if you build a little robot, if you have a robotic arm and you want to control it, that's also considered artificial intelligence, even if it has nothing to do with like building a model or feeding your data, training a neural network. So it's a very broad field that contains a lot of different things. So machine learning is contained within artificial intelligence. So it contains a lot of different models like neural network plus this support vector machine and boosted decision tree model we're going to talk about. So machine learning is smaller than artificial intelligence, but it's still a very broad field. And deep learning is a field that's specifically referring to neural network that we discussed on the last lecture. So the relationship with artificial intelligence, machine learning, and deep learning is kind of the relationship of physics, which is a very broad field that contains a lot of different directions. And nuclear physics is kind of like machine learning, is one subdivision within artificial intelligence. And for example, if I'm working on the search for neutron-less double beta decay, that's kind of like deep learning. It's a subdivision within machine learning. So that is the relationship among those different terms. So the first question we want to try to answer is, so in lecture 1, we started from the very raw Majorana demonstrator data, which is basically the raw waveforms. So this is the lowest level of data we can obtain from our high purity germanium detector. So whenever event come in, that's the raw data we can read from our detector. But do we always have to start from this raw data? Is it possible to start from a higher level data? So the answer is actually yes, you can start from a higher level data, or no, you don't have to always start from the low level data. So we can actually start from a high level parameter with a procedure that we call feature engineering. So remember from the last slide, we discussed about how we can extract different parameters from our single side waveform and multi-side waveform. For example, we can take a derivative of our waveform and we can read out the amplitude we can read out the maximum value of our derivative. That's the A versus E parameter. We can read out how tall our waveform is. That's the energy. We can read out the slope of the tail of the waveform. That's our tail slope. And also we can read out this region of the waveform, like how long does the charge drift within our detector? That's the drift time. So this procedure is exactly the feature engineering procedure. So we have input data that is very high dimensional, is 1,000 dimension, but we perform certain kind of analysis, like preliminary analysis, that we extract 4 values out of this 1,000 dimensional data. So this is the process of feature engineering where we are extracting parameters, just a few parameters from this very high dimensional. High dimensional means low level input. So this kind of data after feature engineering is what we call tabular data because it exactly looks like a table. So the role of the table is, sorry, water is running out of battery again. Thank you. Thanks. Okay, great. This kind of data is called tabular data because literally it looks like a table. So each row is going to be one of our waveform. And for each waveform, we can extract its tail slope, its energies, A versus C is drift time as the kind of the column of the table. So the tabular data is usually of much lower dimension than our raw low-level input data, right? So our low-level waveform is 1,000 dimension, but this one is just 4 dimension. So, and it's obtained through this feature engineering process, which is something you should be relatively familiar if you are working on experiments. So we do this kind of things all the time, like how to extract different features from our raw data. And so basically what we want to do is we want to make sure we extract useful or representative information into just a few quantitative parameters. In this case, our tail slope, energy, blah, blah. And this process, we can actually incorporate our prior knowledge, like what we know about the detector, like which part of this waveform, this event is going to be useful for our task. For example, if we want to reject background, maybe we want to extract this A versus C parameter. If we want to reconstruct the energy of the events, maybe we want to extract the energy parameter, just the height of the waveform. So we can incorporate this kind of prior knowledge when we are doing feature engineering to create the tabular data. So this means our understanding of physics, of nuclear physics, can actually goes into this procedure of creating the tabular data, which is very nice. So that's why sometimes people think this kind of tabular data approach is more physical than just throwing your raw waveform into a black box neural network model and trying to ask it to figure something out. So how can we analyze tabular data? So what kind of model should we use to actually analyze this kind of tabular data? Well, you can use a deep neural network as we discussed on the last lecture, but it's actually not the most, it's not the best model. It's possible to use it, but it's not the best model. Because first of all, deep neural network is particularly powerful for high dimensional data. So it's really good at analyzing those like waveforms, but it's actually tabular data is usually very low dimension. So you extract 4, 5, 20 parameters from each of the waveform. So the dimension of the input is actually relatively low. And also, deep neural network lacks some very useful feature that some non-deep learning, non-neural network model has, which we will show in the next few slides. So we are going to talk about 2 models that you can use to actually analyze this kind of tabular data. And the first model is what we call the support vector machine, or SVM. So the idea of SVM is that you have 2 clusters of data. One is this blue cluster and one is this green cluster. Well, what SVM does is that it draws a decision boundary. It's a hyperplane. So this data is only in 2 dimensions. So a hyperplane in 2 dimensions is just a straight line. So here it draws a straight line between these 2 different clusters. And it maximizes the margin. So the margin is the distance between this hyperplane or this line we draw and the nearest point of both kind of data of both this kind of data cluster. So it's maximizing this, and this. So it's maximizing the margin between the hyperplane and the support vector. And the support vector is defined as the closest data point to the hyperplane. So if you remember what I said from the last lecture, I said a linear classifier is not interesting because it can only draw a straight line between 2 clusters of data. And the support vector machine here, based on what I told you, it looks like it can only draw a straight line between 2 clusters, which makes it very boring. So why do we consider it to be a good model that we can use? That is because we can use a method to make our support vector machine more powerful. And this is what we call the kernel method. So the idea of a kernel method is, let's say if you have this data set where you want to classify this light green dots from the red squares from each other. So this kind of data is impossible to draw a straight line to separate them, right? Because the red dots are kind of surrounded by the green dot. There's no like single plane that can separate them from each other. But what we can do in SVM is to incorporate something called a kernel, which unfortunately, I'm not going to talk about what a kernel is. But the general idea is you project your data into a different dimension. So your data start from 2D, but you kind of project it into a 3D, into this kind of parabola shape. So in 3D, it's actually possible to build a hyperplane. A hyperplane in 3D is a 2D kind of plane. So you can make a decision surface like this, right? In this case, you can actually separate this data set, even though they are inseparable in the low 2-dimensional data. So this is basically one of the advantages of the support vector machine. So basically, a kernel method could transform our data into a space where they are linearly separable. And then we can use this method to separate them, this method, which is a linear classification method, to separate these two clusters of data. So there are some other advantages of support vector machine. First of all, it gives you a very, very clear and even analytical decision boundaries. So when I draw a line between these two clusters of data set, I know the expression of this line, right? I know it's W times X minus B equal to 0. So this feature is impossible in the other models like neural network. In neural network, remember, you just spit out the score for every single event. But you do not know in the original 1000 dimensional space, what would be the decision boundary? What is the exact cut I make to separate these two clusters of data? So this is the advantage is that it has a very clear and analytical decision boundary. That's a model can provide you. Also, unlike deep neural network, which is very data hungry, so it needs a lot of data to train, a support vector machine is very robust against like even a very small amount of training data. So if you train a neural network with say just 10 data points, it's going to give you something crazy. It's going to give you some crazy result that doesn't make any sense. But if you train it with SVM, it's actually going to give you some pretty good results. So in the case that you do not have enough data to train your model, then support vector machine is a really good choice for this kind of task. But remember, if you want to use it, you first need to do feature engineering, and you need to come up with your tabular data format. So the second model that people usually use is called boosted decision tree, which some of you may have heard about before. So basically, boosted decision tree. So I will start by talking about what is a decision tree. So a decision tree makes a classification decision by asking a series of binary questions. For example, let's say this tree is asking you whether you want to go to work or not. So if today is sunny, so basically first it asks you what's the weather today look like. Is it the weather forecast look like? If it's sunny, then we ask, is it humid? If the humid is normal, you go to work. If the humid is high, you don't go to work. And if your answer is today is raining, then it asks, is it windy? If the wind is not too strong, then you can go to work. If the wind is very strong, then you don't want to go to work. So this is how a decision tree is kind of working. So the decision tree model by itself is very, very understandable. So when you make a decision that you do not want to go to work, you can trace down exactly what's the logic that drives you to make this decision, right? So, but it itself is not a very powerful model. So it's what we call the weak classifier. So to increase its performance, we use something called a boosting algorithm, where we kind of iteratively grow many decision trees, one after each other, and we aggregate those weak classifier into a stronger classifier. So the idea is first you feed your original data into your trees and you perform some kind of classification. So some of the data is going to be correctly classified. Some of the data are going to be incorrectly classified, misclassified, false positive or false negative. And then you adjust the weight on this data. So for the data that are correctly classified in the previous pass, you give it less weight. And for the data that was misclassified in the previous pass, you give it more weight and you feed it into another tree. And then you just keep doing this forward and forward. So basically, you keep growing many trees until some point where you feel like your model is converging. Like if you keep training further, you will be overfitting. So and eventually when you are making a classification decision, you aggregate the decision from all the trees that you have grown through this boosting process. So what is the advantage of a boosted decision tree model? So first, it's very powerful. So boosted decision tree and some of the other ensemble learning. So ensemble learning just means you grow many different models and you ask them to make a joint decision. So BDT and the other ensemble learning model usually achieve the best performance in terms of some well-defined tasks like classifying signal from backgrounds. So there is a website called Kaggle, which does a lot of like machine learning challenges. And the BDT is usually the model that achieves the best performance on Kaggle challenges. And it all naturally comes with some level of interpretability if you have a single trees. But if you have many trees, if you have 100 trees, then it's very hard to trace down what's exactly the reason that's behind the model that makes the decision. So I think lastly, I want to mention for the first question, the disadvantage of the BDT and the SVM model is exactly the advantage of the neural network. So BDT and SVM is very slow on high dimensional data. Like if you feed a 1,000 dimensional waveform into a BDT or SVM, you're going to take forever for them to train. But for a neural network, it's actually very good at handling this kind of data. And also BDT and SVM is less customizable. It's difficult to kind of modify them to do some fancy things that we will discuss in the later part of this lecture. And also BDT and SVM cannot achieve more complicated tasks like generating new data. It's basically impossible to do those kind of tasks using this non-neural network models. So before we go to the next question, are there any questions about this? Yeah.
So is data, so not being able to generate data, is it the same as saying that they cannot predict, I guess, things?
It depends on what you mean by prediction. So if prediction means like classification, then it's possible. But what I mean by generated data is like, for example, I want to build a machine learning model that generates a waveform, this 1,000 dimensional waveform from some randomly sampled seed or something like that. So if BDT and SVM cannot do that, you have to do that using a neural network, and we will talk about how to do that in the following slides.
How do you choose what questions to ask in your BDT, or is there an algorithm that comes up with inquiring from the data what you're looking for?
So the answer is you don't choose, you ask the model to choose. So the model will have some mechanism within it that decides. So basically the question has two parts, right? So the first part is which kind of dimension should I ask it? Like so for example, here I decide I want to ask for the feather weather forecast in my first dimension. That's the first thing to decide. The second to decide is well, for this question is kind of ill-defined because it's either yes or no. But in real case, your tabular data contains some kind of parameter. Like for example, if you look at here, so maybe if I'm growing a BDT to analyze this data, first I want to decide which parameter do I want to choose. Oh, I want to choose tail slope, and then what cutting value do I want to choose to make a cut? I want to make a cut of tail slope at 0.5. So basically, at every step, you need to make these two decisions to grow your boosted decision tree. And those decisions are guided by some kind of algorithm which maximize the entropy within. Yeah, basically, yeah.
In some of the cases, we are not able to say which are the labels we are going to use. Can we mix like two different machine learning models, like one to generate the labels and then use a boosted decision tree to do the other steps?
I think I'm gonna briefly cover about that in my following lecture, but it really depends on what kind of label you want to generate. So I think you are talking about something like maybe something like a semi-supervised learning where you have some label data set and you have some unlabeled data set, and you want to generate label from the label data sets over to the unlabeled data set, something like that probably. Is that what you are talking about? Or yeah, that's called semi-supervised learning. Is because you for part of the data you have label, part of the data you don't have label. Is one subcategory of machine learning, which unfortunately I'm not going to go through today. But I will go through something that's kind of in that direction. So, any other questions? Yeah.
Both only work if you want a discrete output parameter, like there's no generalization to a continuous output parameter.
Actually, no. I think actually both of these model actually give you a continuous output parameter. So for example, for the SVM, the continuous parameter can be determined by how far away each dot is from the decision boundary, right? So if it's close to the decision boundary, then maybe the value is low. So it gives you some sort of kind of confidence. And for BDT, well, this is not the best example to show because it is easy. I want to explain the concept, so I use this example. But in reality, what you do is you pick a model, you pick a parameter, and you make a cut, right? You say energy above 50 MeV is one category, energy smaller than 50 MeV is the other category, and eventually you output a value for each of the branches. So here, actual BDT will grow. This is not yes, no. This is actually a flow point number, and you add the flow point number of all your BDTs into a single flow point number. Is a kind of the score, the classification score of your model. So actually, both of these model will give you a continuous output, and you still need to make a cut, as we discussed on the last lecture, to decide what is your signal, what is your background. Yeah.
But does it? I mean, I guess you're still trying to classify signal or background as opposed to get a parameter from your data that could have some continuous range of values. Do you see what I'm saying? I can follow up after.
Okay, sure. Yeah. So, but my point is that both of this model, it takes in this one waveform, let's say, one row of the tabular data, and it output a score, a classification score, let's say, and you can make a cut on the classification score, just like what we did on the last lecture, to perform the classification task, basically.
So can we I don't know, save this in an FPGA and make the decisions like right after we?
Oh, that's an interesting question. I believe there are some work on importing a boosted decision tree on FPGA. I don't know too much about it, but I think it's possible. So some of the LHC people are doing this, I believe. Yeah, but unfortunately, I don't know too much detail about it. Okay, great. I think we should probably go forward because we have 6 questions. I just went through one. So the second question is, my experiment does not produce. Okay, so Marana has this 1000 dimensional short time series data, but my experiment doesn't produce this kind of short time series data, but like Marana does, it actually produces a more complicated high dimensional data from my detector. So what should I use as my feature extractor in terms of that kind of data? So for this, my answer is actually breaking into 3 different parts. So the first point I want to make is that the exact model you want to use to analyze your data actually depends on how you are pre-processing your data. So even if you have a very complicated high dimensional data, it's possible to pre-process it into a 1D time series if you want, with some kind of sacrifice, of course. So I want to talk about another experiment I'm working on called Kamlan-Zen, which actually produces a very complicated high dimensional data. And we will see how we can pre-process it and analyze it using different kind of models. So Kamlan-Zen is also experiment searching for neutrino-less double beta decay. It contains 2 critical parts. So one part is what we call the liquid scintillator. It emits a lot of isotropic light when a particle enters this liquid scintillator region. So it acts kind of like the flashlight of your camera. So this isotropic light escape from away from our detector, and it can be captured by our inner detector PMTs, which is like a sphere. It's spherically surrounding the volume where we hold our liquid scintillator. So this inner detector PMTs basically acts like the camera, the lens of your camera, and we have about 1800 of those inner detector PMTs. So basically the data that's got produced by the Kamlan-Zen is going to be this kind of data. It's going to be each PMT is kind of a dot on this sphere, and when a light enters it, it has a probability to get triggered. So if it's triggered, it produces this kind of information. So it has its position in the spherical coordinates recorded at r, theta, and phi. It has the trigger time, like what time does it trigger, which 1 nanosecond. And also what is the charge that's read out by the PMT. So every single event that comes into your detector will trigger different numbers of PMT. So that adds some additional trickiness. So it's not always the same kind of amount of PMT that get triggered. So what kind of data is this? So, well, it depends on how you are processing it. So if you say, I don't care about the position of my data, I only care about the time. So I can pull out the trigger time of all my trigger PMTs, and I can plot it as kind of like this 1D histogram. And this data is efficiently a time series data, kind of similar to what we encountered in my run demonstrator. And this is oftentimes called a scintillation time profile in liquid scintilla detector, like this one, like the Kamlan Zen experiment. So it's actually a 1D time series. And this is actually what we base our analysis on for a lot of times. The other option is that I say, I don't care about the time. I only care about the position of my PMT. So in that case, I can open up my sphere in the theta phi coordinates, and I can plot it into like a 2D image, as you can see here. So this image is opening up in the theta and phi direction. And you can see each cell has one or more kind of trigger PMTs, and it produces this kind of pattern. Or you can say, I want both. So I want both the time and the position information. So for this, what I can do is that I can open up, I can first slice my data into different kind of time windows. So let's say a time window of 1.5 nanosecond. And within each, I open up this 2D kind of theta phi heat map. So in this case, I'm going to have what I call a spatial temporal data, which is a time series of 2D images. So you can think of it as kind of like a 2D movie that's playing through, certain kind of slides. And lastly, I can say, I don't want to do anything with my data. I just want to pull out these points, R theta phi TQ for the first PMT, the second PMT, the third PMT, and I want to just plot them in my in my space. So this is what we call the point cloud data. So this is and this data type is like very different from the 3 different data type that we discussed. So you can say even for exactly the same detector, exactly the same events, you can choose to pre-process it to different type, and this different type of data, and this data all have very different dimensions and very different features. Yeah, question?
Reprocessing sometimes can make lots of data.
Exactly, yes. So if you are processing your data into a time series, of course you are losing the position information, right? If you process your data into 2D image, of course you are losing the time information. So this is one of the problems. If you want to reach the maximum performance of a machine learning model, you probably want the lowest level of data that contains most, if not all, of the information. So in that case, the spatial temporal type of the Kamlan Zen data will contain most of the information because we are not throwing away any of the information. Yeah.
How is like 4 different from 2? The data type?
Oh, 4 is well, 4 is can I write on the board the water, or is that okay?
Sure.
Yeah. So the data of 2 is basically a 2D kind of a grid, right? So one direction is like theta, and one direction is phi, by opening up the spherical kind of coordinates. So that's 2. And the data type of 4 is going to be something like this. It's going to be an array, and each row of the array is x1, y1, z1, t1, q1, and this. So that's the first PMT. So and then we have a second PMT, x2, y2, z2, t2, q2, and you can have as many PMTs as you want. But remember, each event come with a different numbers of PMT. So maybe the first event has 200 PMT, the second event has 400 PMT. So the first event is going to be an array of 205, the second is going to be 405. So they are totally different from each other. Thank you. So if you have different data type, do we need different model to analyze them? So the answer is, I would say yes and no. So I'm first going to tell you one model that we can use to analyze this data, which is called convolutional neural network. So convolutional neural network, or CNN, is the only model that I'm going to spend a fair amount of time giving you a lot of the detail, because it's a very important model and is generalizable to a lot of different kind of data type. So let's talk about it in some good detail. So first, I want to talk about 2 concepts before I talk about CNN. So the first concept is invariance. So if I have this image A and I rotate it by 90 degrees, so basically first, your machine learning model can be considered as a function that maps from some input space to the output space, right? Let's say our input space is X, our output space is Y. So, your input space can be the waveform and your output space can be the classification decision or the regression entity, basically. So if you have an image A in your input space and you rotate it by 90 degrees, this is corresponding to a certain kind of transformation in the input space, right? It's a rotation transformation. So invariance means if you perform this, if you feed this A before the transformation into your neural network, it gives you output fx. If you perform this transformation and you feed it into the same neural network, it gives you exactly the same output. So this is what we mean by invariance. So equivariance is another concept. So it means if you perform the transformation in X, you rotate your A in 90 degrees, it corresponds to performing the same corresponding transformation in the Y space. So basically is kind of described by this equation. So think about this problem in terms of this classifying a galaxy kind of scenario. Let's say we have some input from our telescope and we want to classify whether this telescope contains a galaxy. But when we are taking images, the galaxy could be at different locations of our telescope image, right? It can be on the upper left, the upper right, the lower left, and the lower right corner. So if we use a fully connected neural network that we learned from last lecture to analyze this 4 images, which all contains a galaxy, but just at different locations. So what's going to happen? So a fully connected neural network assigns a weight to every single pixels of our galaxy images, right? So if the galaxy is on the upper left corner, is corresponding to these pixels. If it's on the upper right corner, it's corresponding to these pixels. So these pixels and these pixels have different weights in your neural network, right? Because you are assigning one weight to every single pixel of your image. Therefore, your fully connected neural network are not translational invariant because you are not using the same set of weights to process, to analyze, to look at this image, this image of galaxies. So the other disadvantage of the fully connected neural network that we discussed on the last lecture is that it actually contains a huge number of parameters. If you are trying to analyze a full HD image, 9020 times 1080, you will need 2 million parameters in your fully connected neural network. And that's actually a lot of parameters to process in a neural network. So to kind of fix this problem, what we can do is we can introduce an operation called convolution, which we are all very familiar with. So a convolution, we use convolution because the convolution is the only linear translational equivariant operation that we know of. So the idea of convolution is to scan a filter throughout the surface of a 2D image. So let's say we have this blue image, this blue square as our input image, and we have this filter which contains a weight. So the weight is exactly as what we described in the fully connected neural networks cases, right? We have a weight assigned to every single pixels of our input vectors, but now we are just putting it into a 3x3 matrix that you can see here. And what you are doing in a convolution is by scanning your filter throughout the surface of the image like this, and at every step of the scanning, you are multiplying the filter weight into the corresponding content with your image, and you are summing them up into these single numbers. So you don't have to scan only one filter. You can scan as many filters as you want, something that you can define yourself. So you can scan n filter simultaneously throughout the same image, and n is what we call the channel of the CNN. So this is by definition. So let's see what's happening if we are using convolution to build a neural network. When we are analyzing this image of the galaxies, where the galaxy could actually happen at different locations of our data. So remember, I have this filter which contains the same set of weights. So when the filter is looking at this image, it's find this galaxy on the upper left, it multiplies with this weight and it gives me a response. Let's say it's 12. And then the filter is moving to the right. But remember, it has exactly the same set of weight, right? So even though the galaxy is at the same location, but since the filter is carrying the same set of weights, it still gives me the same response. If in the first case, it gave me a 12, then in the second case, it's also going to give me a 12, right? Because it's exactly the same set of weight multiplies to your inputs. And then if you move forward, if your galaxy is on the lower left, it's going to give you the same set of weights at this location as well. And lastly, if your galaxy is on the lower right, it's going to give you the same set of weights. So regardless of where your galaxy is upon the image, it's gonna give you the same kind of value as outputs in a convolutional neural network. So this is why it is a very useful model to analyze image data. So just a few more definitions. So the input to your convolutional, to the layer of a convolutional neural network is what we call the input or input image, and the output is usually what we call the feature map. So due to the nature of a convolutional neural network, it's very clear that usually our feature map is smaller than our input image, right? Because we are scanning this filter 3x3 filter throughout the surface of the image, and for each step of scanning, we are multiplying and summarizing them into just a single value. So the advantage of convolutional neural network is first is locality. So your inputs to the filter is only restricted to certain regions. And in an image, usually the nearby regions contains a useful kind of information that we want to look like, right? For example, this galaxy image, all the nearby pixels on this plot contains the useful information about the fact that there is actually a galaxy. Okay, this is a little bit slow. So the second useful property that the neural net convolutional neural network is actually translational invariant. So regardless of whether the galaxy is on the upper left or on the lower right, it's gonna, since the filter contains the same set of weights that scans through the surface of the image, if you multiply the weight and you sum them up, it's gonna give you exactly the same value, right? So the same filter can be applied throughout the entire input. So these are the advantages of convolutional neural network. So so as I mentioned earlier, a convolution of a convolutional layer can usually decrease the size of the input image. So your input is 5 times 5, and if you scan a 3x3 filter, and every time you scan it with a 2x2 stride, so each time it move, the filter move by 2 units. So in this case, your output is a 2x2 feature map, as you can see on the left. But it's also possible to make your feature map larger than your input image. So to do this, what we do is we do something called zero padding. So we add a lot of zeros to the circumference of your input images. And you can see in this case, your input is 5 times 5, but your output feature map is actually 7 times 7. So this procedure is what we call the deconvolution, because instead of making the feature map smaller, it's actually making the feature map larger. So okay, let's see. Any questions about the convolutional neural network? Yeah.
Would you ever want to do deconvolution?
You will see that in the next part. Yeah. Question? Sorry, the gentleman in the back.
Yeah, the weights of the filter are random, but the size of the filter you decide, right?
Yes, it's something you decide.
It's not 3x3, 4x4.
I mean, it really depends on the problem, but there has been some research showing that a smaller filter size and multiple layers can reproduce the effect of a larger filter size. So usually you want to use the small filter size, but you want to stack like a very deep, like many layers of convolution. Sorry, pardon?
Segment filters.
Well, you can have multiple layers, just like the fully connected, right? So each layer will carry a filter of different size. So the first layer has 3x3, the second layer has 4x4, the third layer has 5x5. So you can stack multiple layers with smaller filter size. Usually that works better, kind of. Yeah. Yeah.
Sort of piggyback. Just
Yeah.
about the filter. So filter weights are randomly determined, or do people manually determine?
Well, so at the beginning, they are randomly determined. But then during the training process, which we discussed on the last lecture, we change the filter width to best achieve our task of either classification or regression, just like what we said on the last lecture. Yeah, question?
If like training data set is small, what are the techniques we use is like try to modify our input like data. But in this case, since the filter will give us like the same value, what you can do in that case?
Well, the filter is going to give you a value that best satisfies the task you want to achieve, right? If you want to do a classification as the end of the neural network, then this filter is going to change its value to adapt to eventually achieve the best classification performance in after training. So its value is determined after training. I wouldn't say it's fixed. Is trained to achieve the task. Yeah, basically. Okay, so let's keep going. So convolutional neural network is a very, very nice model because it is very easily generalizable to different kind of tasks that we can achieve. For example, if we want to analyze this time series data from Compton, we can use a 1D convolutional neural network. If we want to analyze a 2D image, we can use a 2D CNN. If we want to analyze the spatial temporal data, like the 2D movie, we can treat time as a third dimension, right? So this is basically become a cube, and we can use a 3D CNN. So it's very, very generalizable. So the only data that it cannot really analyze is this point cloud data. So for this one, it's better to use something called a point net or graph neural network. But unfortunately, I don't have time to go through what this is in today's lecture. So in summary, CNN is what I call the general purpose model because it can really be generalizable to multiple dimensions. It can analyze 1D data, 2D data, 3D data, or even 4D data. So for 4D data, you can use the 3D CNN and you can use the channel because remember, CNN has an additional channel dimension, which is you use multiple filters to look at the same inputs, and you can use the channel dimension as an additional dimension. And also CNN is actually very efficient to build what I call the baseline model. So if you have some data, you want to build a machine learning model, but you don't know what to use, just try to build a CNN and is basically going to give you some kind of baseline classification or regression performance that you can compare against your traditional algorithm or some more advanced algorithm that you want to build in the future. So, but is there a way to further improve on this? So after building a CNN, we have a baseline model, but is there a way to further improve on its performance? Well, the answer is yes. We can enhance the neural network performance by encoding additional symmetries in our data using something we call the geometric deep learning. So one of the example I want to give is kind of like the sequential symmetry in a time series data. Like for example, when we are analyzing this spatial temporal data, which is like a 2D movie, there is actually a sense of order. So the second frame actually comes after the first frame. So how can we encode this kind of order information as a symmetry into our neural network model? So we can use something called a conv-LSTM model, a convolutional long short-term memory network. So the idea of this network is that you feed in each frame of your 2D movie kind of sequentially into this model. So when you feed in the first frame into the model, it gives you something called a hidden state as output. So that's the first hidden state, which contains information from only the first frame. And then you can sequentially feed in the second frame, and it's going to give you a second hidden state, which contains the information from both the first and the second frame. So it's going to be looking at the correlation between the first frame and the second frame. And you can keep feeding in more and more frames until you reach the last hidden state, which contains the information from all the frames. So this is very efficient in terms of handling the actual spatial temporal data because one of the dimensions is the time, and the time actually has a sense of direction, right? It can only flow forward, not backward. conv-LSTM has convolution to handle this kind of 2D image feature, but you also have the time series data where you for each time sample you only have a single value instead of frame. So in this case, you can use a LSTM model, a simple long short-term memory model without convolution, and is very efficient in analyzing, like for example, the waveform data produced by my Marana demonstrator, because of the same reason I mentioned in telling you about the conv-LSTM. So the other important symmetry we can encode in the Kaplan Zen data is a spherical symmetry. So remember, our detector is a spherical detector, and it produces actually a spherical image instead of a flat image. So why is that important? So let's think about this situation where we have a circle on the surface of a sphere. So if this circle is facing upward and you open up your theta phi heat map like this, your circle looks like a straight line. But if your circle is actually living on the belly of your sphere and you open up this theta phi heat map, you actually have a circle. But this is the same circle despite the fact that we are rotating our detector, right? We are asking the circle to face different directions. So to kind of so if you feed it into a normal convolutional neural network, you are basically trying to tell your neural network that the circle is the same as a straight line, which doesn't make any sense. So what we can do to address this situation is using something called spherical CNN. So it actually can analyze data using the SO3 rotational symmetry and analyze it in a rotational invariant manner. So the model can be understood in this way as an analogy with a normal CNN. So in normal CNN, we are scanning this 3x3 filter throughout the surface of our image, and our output is also a flat 2D kind of feature map. So in a spherical CNN, your filter is actually covering the entire surface of your spherical image, but it's only covering it from certain angle that you are viewing it, basically. And the scanning process is equivalent to rotating your spherical image into different directions using the Euler angles. And that's why the output of the spherical CNN is a 3D cube spanning the Euler angle space, alpha, beta, gamma, instead of just the 2D, instead of a 2D feature map. So this is equivalent as simultaneously viewing the same image from all possible directions, all possible angles, including both when it looks like a straight line and when it looks like a circle. So by doing this, you will actually be able to address this situation where the same image, this is the same event despite their orientation are different. So this is part of the geometric deep learning that I mentioned, and it's actually can improve the performance of our neural network model. So let's see how it can actually improve the performance of our model. So in the Kamlan experiment, we actually performed some computer simulation for our signal versus background events. And we actually vary two of what we call the information parameter called photo coverage and quantum efficiency. So this two parameter controls how much information we have in our simulated events. When we have those parameters both at 100%, we have a perfect detector where every single photon got captured, and we have this very nice kind of pattern of hits on our theta phi heat map. And when you reduce the photo coverage, you have something like this. When you reduce your quantum efficiency, you have something like this. And when you reduce both of them, you have something like this. So you can see this is kind of the real case, but its information is much less, right? This is much more scattered compared to the perfect case where you have this very coherent kind of pattern of scintillation light. So basically this allow us to benchmark our model performance under kind of different input conditions, where if you increase these two parameters, you have a better detector and you have more information in your data. So we are actually comparing the performance of our spherical CNN model versus the normal 2D convolutional neural network model that we mentioned at different values of these information parameters. So we can see the comparison is actually pretty different. So first, if we are using this spherical geometry in our detector, we are having much better performance across the entire mass of different photo coverage and quantum efficiencies. And also we can see that by encoding the symmetries, our model is much more robust. So if you are using a normal convolutional neural network, you have these situations where if you increase your information parameter, your performance actually decrease. Your performance becomes worse when you are introducing more information into your data. This is counterintuitive. It means your model is not robust. It's not extracting all the information you are introducing. But this kind of behavior disappears if we incorporate the spherical symmetries using geometric deep learning. Yeah.
Disappear completely, or are there still a couple of apparent?
Well, at least not visible with our eyes. We also did some very preliminary quantitative study, but it's difficult to quote like a very rigorous metric to describe robustness, I would say. Yeah. Okay, I think I almost finished. Yes, so I finished this part. So any questions about the second question in general? Okay, great. So then let's go to the third question, which is, can I use deep learning for event simulation? So if I want to actually generate some events instead of just make a classification or regression decision, so how can I do it? So the answer is yes, we can actually use something we call the generative model. So I'm going to talk, so I listed three of them, variational autoencoder, generative adversarial network, or diffusion model. But unfortunately, I'm not going to have time to talk about diffusion model. So I'm only talking about the first two. So first, let's think about what kind of task is event generation. So remember in this kind of flow diagram that I showed yesterday, so what we have is we have input data, which is of very high dimension, is like, let's say a 1000 dimensional waveform. We feed it through a feature extraction network and we encode it into a representation of very low dimension, like 32 dimension, for example. So now, but if we want to do event generation, we actually want to do something kind of reverse, right? So we want to start from a low dimensional representation of our data. For example, we want to start from the energy of the event, the nature of the events, like is it a neutron, is it alpha particle or something, and we want to feed it through what we call the decoder network, and we want to produce the waveform or the spatial temporal data or whatever data that your detector is actually producing. So it's kind of a reverse process. So it's the input is small and you feed it into a decoder network and it give you a larger data, which ideally would look similar to your input data, right? So how can we do this? Well, the answer is we can actually build something called a convolutional autoencoder. So the idea of this model is to concatenate two convolutional neural network back to back. So so the first part is called the encoder, which is exactly what you do in the feature extraction network. You have some you have your input image or your input waveform, and you encode it into a representation. And the second part is why we need this deconvolution layer, which takes in a smaller input and give you back a larger input. So if you do this deconvolution, you can actually output something that's at the original size of your input image, right? For example, if your input image is 1000 times 1000 and you encode it into a 32-dimensional vector, then through a series of deconvolution, you can reproduce an image of size 1000 times 1000. So this is what we call the reconstructed image. And what you do in convolutional autoencoder is you are minimizing the MSE loss. You are minimizing the difference between your reconstructed image and your input image. So you are training to so basically the idea is that each image is encoded into a low dimensional representation, and then it can be reconstructed from the representation by this decoder network, which contains a series of deconvolution layer. And but unfortunately, convolutional autoencoder is not a generative model. The main reason is because you cannot sample from the latent representation space. So the representation can be considered a single number. So it's basically encoded from the input image. But if you deviate from it a little bit, then its output reconstructed image will completely make kind of no sense. So if we want to generate something new, if we want to generate some image that we have not seen before, the thing we have to do is that we have to be able to sample from this latent space representation, or in other words, we have to make our latent space representation become a distribution, for example, a Gaussian distribution, instead of only giving you a fixed number. So this is why we need this model called variational autoencoder. So in convolutional autoencoder, your representation does not follow any particular distribution. It can be some, it kind of like scattered. So every single image or data you feed into your autoencoder gets encoded into like a scattered point in this very high dimensional 32-dimensional space, but it doesn't follow any distribution in particular that we could understand. So this means we cannot sample from the distribution to generate data that we have not seen before. So variational autoencoder add additional loss beyond MSE loss to regulate this latent space, to regulate this representation so that it follows a particular distribution. And if it follows a particular distribution, it means we can sample from it. So this loss we add is called KL divergence. It basically measures the distance between two different probability distributions. And the idea of this KL divergence loss is to make sure that our representation follows a multidimensional Gaussian distribution. So if it follows this distribution, then we can sample from this distribution to get a new representation. And then we can feed our representation into our decoder network to generate a new data that we have not seen before. So this is how we achieve a generative model by using autoencoder plus this KL divergence loss. So any questions about this? Yeah.
How do you make sure that this kind of simulation can produce some physical events?
Well, so the way you are making sure this is by the MSE loss. So basically, you make sure your input image and reconstructed image are the same when you are training. So the MSE loss, remember, it calculates the distance of every single pixel of your image or your waveform or whatever. So during training, it makes sure that these two are exactly the same, ideally, but when you are running your model to generate new events, you are sampling from the Gaussian distribution to generate an event that you have not seen before. So ideally, so it is almost like an interpolation process where you have every single point that's you train to kind of match exactly between the input and reconstructed, and then you are sampling the points within your representation space that has not been seen before by a neural network. So this is how you are generating. But regarding your question about how to make sure that it follows the physics distribution is basically guaranteed by this kind of MSE loss. But I would say it's never like purely guaranteed because to actually understand how well your generative model is working, you have to actually do the evaluation. You have to plot these two kind of events together and try to understand if they are actually the same, right? So any other questions about this? Okay, great. So the other generative model I will talk about is relatively, I would say, more famous. It's called a generative adversarial network, or GAN. You might have heard about this. So the idea of GAN is actually very interesting. So it has two sets of network. So it directly starts you starting this like event generation process from a pure random noise. You know, it can be some kind of Gaussian noise, and you feed it into, let's say, a Gaussian noise of like 32 dimension, and you feed it into a series of deconvolution network, and they give you a 1000 dimensional waveform or a higher dimensional image, which what we call the fake image that we generate from this pure random noise. And in the training data set, you also have some real image that you collect from your detector or some other means, and you train a discriminator network that's its goal is to try to figure out whether this image was generated, was fake, was generated from noise, or is actually a real image from our training data set. So during training, that's why it's called the adversarial network, because during training, the generator network and the discriminator network is actually fighting each other, right? They have exactly opposite goals. So your discriminator network is trying to figure out, is trying to do a classification and tell me whether this image is real or is fake, is generated. While your generator network's goal is to fool your discriminator network, is trying to generate the image that cannot be discriminated by your discriminator network. So these two models during training will fight each other, and they will eventually reach some kind of convergence where the generated image is no longer distinguishable by this discriminator that we built. So this is the idea about how we train a generative adversarial network. So question, yeah.
So when you say random noise, you say also that Gaussian random noise. What do you mean by it?
Well, it can be, for example, a 32-dimensional vector that's sampled from a 32-dimensional Gaussian distribution with mean 0 and 1 standard deviation. Or it can be a uniform random noise. It can be any kind of random noise. It's something that you define. Yeah. Any other questions? I want to make sure that everyone understands how a GAN is working, because this idea of adversarial training will be brought up many times in the future slides. So yeah.
So after we're done training these two competing
Yeah.
networks, if we wanted to generate something, we wouldn't care about the discriminator network. We would just be using the generator and then taking that out.
Exactly, yes. So, and then you can sample from this random noise. If you have a uniform sample random noise, you can just keep sampling from it, and you can keep generating kind of new images, right? Okay, great. I assume everyone understands how GAN works, and let's keep moving forward. So the question 4 is, okay, now I train my machine learning model with simulated events, you know, either from, for example, a Gen 4 simulation, or from my generative model, the one that I described. So, but my simulated events still look different. It's still not exactly the same with the actual real detector events I collected from my detector. So in this case, what should I do? So there are actually 2 ways to solve this problem. The first way I would argue is to build something called a cycle GAN to perform what we call the unpaired translation between your simulation and your data. So to translate your simulation to a state that is very similar or even indistinguishable to your data. And this is achieved by the adversarial training idea that I mentioned in the GAN model. So let's think of event simulation, simulated events and real events as kind of 2 different languages. So the idea of simulation tuning is to build a model that can translate our simulated event to a state that is almost indistinguishable to the real detector events. And ideally, we will train our translation model between a paired events, but those paired events are very difficult to obtain, because if you have paired simulation and data that correspond to exactly the same physics, then you don't even need a translation, right? You already know what the detector events looks like. So let's think about this as in terms of language. Let's say I'm trying to translate English to Chinese. So if I have exactly paired data between my English word and Chinese word, then I can just feed in my English word to the model and get out and train it to reproduce this Chinese word. So this is the ideal case, but in real case, what I have is not this. It's something like this. So I have a whole bunch of English word, I have a whole bunch of Chinese word, but I don't know which one corresponds to which one. So this is the unpaired translation situation between our simulation and data. This is usually what we have, right? We simulate some data, we collect some data from our detector, but we don't know what are the correspondence, what are the one-to-one correspondence between these two. So in this case, we can still perform a translation. So the idea we are doing it is by building two sets of translation network. So the first set of translation network, it can just, the translation network can just be an autoencoder style where it takes input and output at the same dimension. So the first set of network try to translate English to Chinese, and it's taking the word cat and it translated something to something like this. And then we have this discriminator network, which asks a question, which try to tell whether this translated word is real or fake. Does it look like an actual Chinese word, or does it look like something different? So this discriminator network is going to be doing this GAN style kind of training with my translation network to make sure that the word I translated is actually similar to an actual Chinese word. And then I feed this translated word back to my Chinese to English translation network. And ideally, it should translate back to exactly the same word, which is cat, right? So this is why this model is called cycle GAN, because it's going through a cycle of two networks that translate English to Chinese and then back to English. And it also doing a GAN style adversarial training to make sure that this word is indistinguishable from the actual Chinese word. So does this kind of unpaired translation actually works? So we can look at its effect on some of the Marana waveform translation. So we can see that our input simulated pulse, this red pulse, is actually a multi-site waveform, and after we feed it into our trained translation network, it's output this blue pulse, which is still a multi-site model, but now it looks more similar to our detector data, which has this kind of decaying tail slope. While in the simulation, we have like a flat tail slope. So it's actually capturing the physics that's happening in our detector. But you can see that our simulated pulse and detector pulse are not corresponding to each other, right? Because our simulated pulse is a single-side event. It only have a single step, while our simulated pulse is a multi-site step. So this model makes the translation, but it also preserves the physics nature of our evidence. It still keeps the multi-site kind of nature of our pulse. So this is the first way of dealing with the discrepancy between simulation and data. That is by translating simulation to a state that is similar or indistinguishable to the actual data. So the second way is to actually modify our network. So this is something we call domain adaptation. So doing a domain adaptation between simulated data and real data when we are training a neural network model. So domain adaptation is a subcategory in a big field in machine learning called transfer learning. So to understand transfer learning, I will need to introduce two concepts to you. So the first concept is called source domain. So the source domain is a domain for which our training data is located within, is drawn from. So in the source domain, the data are typically labeled. So basically in the language of nuclear physics, the source domain is basically our simulated data, because when we are simulating a detector event, we know exactly what it is. So that's why we call it the source domain. And the target domain is where we want our model to be adapted to. We want our model to be applied to. Given that it's different, it can be a little bit different from the source domain. So the source domain, in the target domain, the data are typically unlabeled and it looks different from the source domain. So in the context of the language of nuclear physics, our target domain is basically the real detector data that we produce from our nuclear physics detector. So basically here I want you to basically just draw an equal sign between this. So the source domain is simulated data and target domain is the real detector data for an easy understanding. So lastly, a task is defined as either a classification or regression task that we already discussed on the last lectures. So given this term, we can actually split task into these different kind of categories. So the first is asking, is the source and target domain data the same? So if they are the same, and then we are asking, are we doing the same task on the source or target domain? If both answers are yes, that's our usual kind of supervised learning setup. But if our source and target domain data looks different, that is, if our detector data and simulated data actually looks different from each other, but we are still doing the same task. We still want to do, say, signal background rejection, on source domain and target domain, we still want to train our background rejection algorithm on the source domain data, and we want to generalize, we want to apply it to the target domain data. So that's no on the source target domain agreement and yes on the task. So this is what we call the transducive transfer learning. And this is exactly what domain adaptation is. So I'm gonna only tell you one algorithm that can do domain adaptation. So let's start with our simulated data, which is located in the source domain. So we have, when we simulate our detector data, we have the label. We know exactly what event we are simulating. Is it a signal or is it a background, right? So I can just do exactly the same thing as what I told you on the last lecture. I feed my simulated data into a feature extractor. It produces a representation of simulated data. And then I feed it through the task module. It produces the output. And then I do the same training, right? Because I know my label, I can calculate the loss function. I do backpropagation to train my feature extractor and the task module. So this is exactly what I talked about on the last lecture. But now we have some other data. We have our real detector data, which come from the target domain. So that's produced by our detector, and it can look a little bit different from our simulated data. So that's something we assumed within our machine learning model. So for this one, we can feed it into the same feature extraction network to produce a representation of the real data, but we cannot go any further, right? Because we do not have label for this data from the real detector. So in this case, what we can do, we can build another discriminator network, which perform a real fake classification, adversarial training between your representation of the simulated data and the representation of the real data. So this is exactly the same as what you did in the GAN model. So you want to train this model to a point that the representation of the simulated data is no longer distinguishable from the representation of the real data. So by doing this, you can actually make sure that even if you are applying your model to the real detector data, it still give you reasonable outputs in terms of classification or regression. So given this kind of setup, we have two loss functions. One is a traditional kind of classification regression loss in our task module that we use to train our neural network. And the other loss is adversarial loss. So this is exactly the same loss as we discussed in the GAN model that makes sure the representation of simulated events and representation of real events are indistinguishable from each other. So this model is listed in this paper. So if you're interested, you can read more about it from the paper. Okay, so let's see, before I go forward, any questions about this? Yeah.
Simulated data and real data are the same structure, like the same level of complexity.
Yeah, they are usually the same structure, yeah.
But can we use transfer learning to go from simple data structure to more complex, like from simple physical formula, and use transfer learning to a complex physical formula?
Well, but is your input data still the same dimension?
No.
So in that case, that's not domain adaptation. That's probably this, right? So you are doing different tasks on your source data and targets on your target domain. So that's a different task which I don't have time to cover for today. But we can talk after the lecture if you want to discuss more. Okay, so let me try to finish everything because I only have 15 minutes left. I have 2 more questions. The next question is, okay, I'm done with simulation. I don't like simulation. Is it possible to directly train my model on real data without bothering about simulation? So the answer is yes. So, your real detector data is oftentimes unlabeled. So you do not know exactly what those data are. Unlike simulation, when you are simulating events, you know exactly what they are. So in this case, we have to adopt something called unsupervised representation learning, which is very different, very different setup with what we have done before, where we have the label data. So in supervised learning, the task is actually defined by the label if you think about it. So when we have the label of signal versus background, 1 versus 0, we can use this. We are basically training our model to be a background cut. When our label is energy, we are training our model to become kind of an energy reconstruction filter. And when our label is position of the event, we are training our model to become a position reconstruction filter. This is a typo, sorry about that. So, but in terms of representation learning, we have something that's really different because now we do not have a label. It's impossible to define what task we want to achieve, right? So in this setup, since there is no label, the goal is to learn a good representation. Remember, representation is just a 32-dimensional vector that's much smaller than your input data that would encode important informations in our data. So this representation, since there's no label, there's no associated task, but rather the representation is what we call the task agnostic, and it can be generalized to different kind of tasks, either classification or regression or something else that we want to achieve. So how do we know which information are important? Which information should we encode into our using our representation learning algorithm? So the answer is usually the pixel level detail information are not important. So how do we know that? Well, there is a very interesting experiment that people in the cognitive science do. So basically what happens here is so first we ask a student to draw a $1 dollar bill without having a $1 dollar bill in front of the student. So the student is purely drawing from their memory. So in this case, the bill that they draw is something like this. But on the right, we have the same student doing the same thing, but with the dollar bill present in front of the student. So in this case, the student is drawing the dollar bill something like this. So we can see that if you compare these two drawings from exactly the same student, you can see that a lot of the details like these frills on your dollar bill, these fine details at pixel level is actually not important. So what the student actually remembers in their brain when they are drawing the dollar bill are those, the $1 dollar sign that actually separate this dollar bill from different dollar bills, right? So these kind of information that we actually store in our brain when we are learning is what we call a high-level semantic information that distinguish different dollar bill from each other. So that's why we can use a method called contrastive learning to extract this kind of high-level semantic information. So the idea of contrastive learning is basically learning by comparison. So here I'm gonna very quickly introduce one contrastive learning algorithm, which is called a deep info-max. So how this algorithm work is we first have an input image, let's say an image of dog. We feed it through a series of convolutional neural network to output a feature map, and then we feed it through a series of fully connected neural network to produce a feature vector, let's say a 32-dimensional feature vector. So the feature map is usually much larger than the feature vector, and the feature vector is the representation we want to learn. So basically, the representation space is going to be the probability space where the feature vector lives in. And if we are doing representation learning, we want our feature vector to encode all the high-level semantic information from the feature map if it is well trained. So the way we are training our model is using a concept called mutual information. So you can think of mutual information as kind of a measure of correlations between different vectors. So basically here we want to measure the mutual information between your feature map, which is large, and your feature vector, which is small. So basically the training is done using contrastive learning. So you are grouping your event into pairs. So when you are grouping your events into pairs, there are two possibilities. One possibility is a pair of events are from the same image. The other are the fact that they are from the different image. So if the two input are from the same image, you want to maximize the mutual information between the feature map and the feature vector. And if the two input are from different image, you want to minimize the mutual information between your feature input, feature map and the feature vector. So I think this is a little bit counterintuitive. So feel free to come and ask me about this after the lecture. So let's see if this model actually works. I'm showing you some of the results on the Marana demonstrator waveform that's I showed you on the last lecture. So each dot is a representation, is this smaller vector that we extracted using this deep info-max algorithm and without any label. So because this is learning by comparison, it does not need labels for your data. So you can see it actually follows a certain kind of geometric structure that it has this kind of band that's kind of curling around like this, and it has this little ring island that's kind of isolated. So if we look at points, so we can look at some of the waveform at different locations of this band. If you look at the trend from A, B, C, and D along this longitudinal direction of the band, you can see it takes longer and longer for the waveform to reach its maximum, right? So the length of the band actually represents the physics, actually represents the drift time of the waveform that's happening in your detector. So if you compare 2 points at the same longitudinal location, but at different width of your band, that's point D and E, you can see they takes the same time to reach the maximum, so their drift time is roughly the same. But all the events in D are single step, like single site like waveform, and all the waveform in E are multi-step, multi-site like waveform. So basically, the width of this representation represents the single site versus multi-site effect that I have shown you earlier in my talk. And lastly, we have this ring island structure that is isolated from the rest of the mainstream data. So if we pull out the waveform in this isolated ring island, we can see they have this kind of very slow curving, very slow like turning edge. So this is actually because of the surface effect. So we can see that without any label. So I just throw this data into my contrastive learning algorithm and ask it to figure something out for me. And it actually figure out all the physics that's behind the scene, all the physics that's hidden in my germanium detector. So yesterday, one of the gentlemen asked this question. So if I don't want my machine learning model to just mimic, to just reproduce some of the label I provide you, but I wanted to be able to discover some new physics, some new information that's hidden in my data. So this is going to be the way to go, right? So this actually trains over a data set without any label, and it kind of outlines all the physics structure within the geometric shape of the learned representation space. Okay, so the last question is actually one of the most important question, I think, is also a question I got a lot of the time when I'm doing a machine learning model, which is I build a machine learning model within my collaboration, attempt to use it for my analysis, but my collaborator do not like it. They keep telling me you cannot trust the machine learning model's decision because the machine learning model is a black box, right? So in this case, what should you do? What should you show your collaborator that the machine learning model actually works, is actually a reasonable things to use for the physics analysis? So I think to answer this question, we have to follow kind of 2 steps. So the first step is to perform good uncertainty quantification over your machine learning model. So you want to report uncertainty for the machine learning model's decision. And as physicists, we are actually pretty good at doing this. So I'm going to talk about kind of 2 methods. So one method is called bootstrapping. It's more like a traditional method. So the idea is you have some training data set, some training samples. You perform a bootstrapping over the data set. So bootstrapping just means randomly sample with replacement. So you pull a data out and you put it back, and it's possible to. So when you are doing bootstrapping, it's possible to have the same data within your data set. So you can bootstrap many different times. Let's say you bootstrap like 100 different bootstrap data sets, and you use this 100 data set to train 100 different neural network models. And this model can be your model trial 1, 2, 3, and model trial N until model 100. And then you can evaluate your model performance on every single trial of your model, and then you can use it to quantify a statistical uncertainty. And you can also quantify systematic uncertainty by varying your model structure or varying some of the parameters in your data, right? So as physicists, we are already very familiar with this kind of traditional method. But another thing I want to bring your attention is the second category, which is something called uncertainty-aware machine learning model. A machine learning model that can directly give you an uncertainty when you are training it or when you are using it to make a prediction. So one of the model I want to discuss is called a Gaussian process. So a Gaussian process model, let's say I'm trying to use a Gaussian process model to make a regression. So the idea is I have some input and I want my output to, I want to regress it so that I'm fitting it to certain output data points. Let's say that's the task I want to achieve. So what we will start by a Gaussian process is we first start from the distribution of all the possible functions. So if I say I want a collection of all the possible functions that could fit my data, then the function could look like a mess, right? It would look like a spaghetti or something that it can follow. It can be anything. But I don't want it to be exactly anything. I want it to follow certain kind of distribution. So basically the idea is I want my function to follow a Gaussian distribution. And the way I'm doing this is by defining two metrics. One is a mean function. So the mean function is basically the mean of all the possible functions that could fit my data. And the second is to define a covariance function, which is what I call the kernel. So this measures the correlation of the function at every two possible input points. So by doing this, I can define what I call the Gaussian process, where my function is actually a distribution of function that follows a Gaussian distribution. So why is this model useful? Because I can actually output uncertainty when I have this kind of Gaussian process model. So let's say before I have any data sets, my function can follow anything. It can be any like arbitrary kind of shape. But if I made the observation here, you can see, then I'm basically during training, when I'm putting one point here, I'm filtering out all the possibilities where the function is not passing through this point, right? So this, if a function goes something like this, it's got filtered out because it's not passing through this point. We know it's not possible. So it collapses at this point into zero uncertainty. So we are 100% certain that this function should take this value here. And similarly, I can put more points here. So the beauty of this Gaussian process model is that when you have a measurement at certain points of your function, you will have zero uncertainty. And when you are a little bit away from where you have a measurement, where you actually have a data point, you have a small uncertainty because it's likely that this point is nearby, is closer to your actual observation, which is light in the red. But when you are very far away, when you are at this point, you have no idea what the actual value of your function is, right? So your model actually output a very large uncertainty. It says, okay, I don't know what the actual value should be at this point. So I give you a very large range. So I give you a large uncertainty with my mean prediction here. So basically, when you are using a Gaussian process to perform, for example, energy regression task, at every single point of your function, it's gonna give you a value come with an uncertainty that follows a Gaussian distribution. So this is what we call the uncertainty-aware machine learning model that would naturally give you uncertainty after training. So this is only one of the examples, and we have some other uncertainty-aware machine learning model, include the Bayesian neural network, Monte Carlo dropout, deep ensemble, and quantile regression, which I do not have time to go through today. So the next thing I want to talk about is interpretability. So the idea of interpretability is to understand the reason behind how neural network actually makes decisions. So I'm actually going to skip this because I don't have enough time. So let's talk about a very simple method called saliency map. So saliency map is a gradient-based interpretability technique. It's going to actually be able to help you kind of highlight the part where your neural network is relying on to make a decision. For example, here is a classification of different animals. You can see when it's classifying this bird is actually looking at his body, like it's actually so the saliency map actually shows which part of is looking at for this bird, right? Like for this different bird, it's always looking at the body of the bird. So it's giving you the information which part of the input image is actually contributing to your classification or the regression decision. So how can we draw a saliency map? So remember, when we are training our neural network, we feed our inputs into a neural network model and we predict a prediction. And then we calculate the loss function. We perform a back propagate to calculate the gradient upon our weight of our neural network. And eventually we update our weights using the optimizers. This is how we are training a neural network we went through in the last lecture. So computer saliency map follow a very similar approach. So the idea is you also perform the forward pass, which is nearly the same. You feed your input through your neural network and you make a prediction. But here you do not calculate the loss. You directly carry over your prediction to your backward pass and you back propagate it through all the way through your neural network to your input. So you are calculating your gradient not on the weight, but on your raw input x. And then you plot this gradient. And that is how you are getting this kind of heat map on your machine learning model. So this is going to tell you which part of your machine learning model is bringing most of the gradient when it's making this prediction decision. And this is a very useful way, very simple but useful way to interpret the decision of a machine learning model. So the last thing I want to talk about is another way of interpreting a machine learning model, which is called Shapley value. So Shapley value is what we call the black box interpreter. So the idea is that it can be used to interpret any machine learning model. So you can train a machine learning model, and then you can give it to this Shapley value, this shape package, and it's going to be able to help you figure out which component of your input is the most important part in terms of making the decision of your model. So this Shapley value interpreter actually works better on the classical machine learning model instead of a deep neural network because it's actually very slow. So it's better to work with this kind of tabular data after feature engineering. So you have a very low dimensional input. So Shapley value is a concept from correlational game theory, and it's basically like a lot of players playing a game together, and they are allowed to kind of collaborate each other. That's a correlational game, and it represents each player's contribution to the total surplus or deficit of the game, given that they can work collaboratively, that they can collaborate together. So what a Shapley value can do is that it can generate something called a force plot. I think this is the name that's come up by computer scientists which never learned physics. So it's actually a free body diagram. So the idea is that for each of your input events, your Shapley, the Shapley value will produce basically a force plot, which is the free body diagram. So each value of your force plot is actually acting as a force that's either driving the output to a lower value, or it acts like a force that drives the decision of your neural network model to a lower value, or to a lower value that's more background-like, or a higher value that's more signal-like. Like for example, and eventually the value after applying all the force is going to reach some equilibrium along this number axis, and that value is the one we output to our machine learning model. So basically, for example, if you look at this single event, this single data point that's I interpreted using the Shapley value, we can see that this event was classified as a background because we have a very high negative push from the amplitude versus energy parameter that we extracted from our feature engineering process. So that is telling me that this parameter is trying to push my decision is supporting the decision that this event is a background event, while the noise parameter actually is voting against it. It's saying this event is more signal-like. So the Shapley value actually allows us to do something that's very interesting. It's called learning from the machine. So we can learn from a machine learning model some of the physics that we previously did not discover and use it to improve our physics analysis. So for example, what we can do is that we can select the data that was correctly classified by our machine learning model, but it was misclassified by our traditional method, the traditional cut that we built. And we use the Shapley value to interpret it, and we see what's the driving factor of this decision, and which direction is it voting toward. And then, so let me give you one example on the Marana demonstrator experiment that I'm working on. So in Marana demonstrator, we find this cluster of events that is actually what we call the surface alpha background. It was successfully rejected by our machine learning model, but it was actually accepted by our traditional surface alpha cut. So we look at the Shapley value of this event, and we find all of these events has very low drift time, and the machine is actually rejecting, is actually giving it a very large negative force that pushes this event to be background-like, based on the fact that they have a very low drift time value. And based on this factor, we actually understand that these events are the event that is near the point contact where we read out our detector information. So it's actually, so our cut actually relies on the what we call the passivity layer of our detector. But if the event is happening here, it's not going through the passivity layer, so it's missing. So it's missing the component that we can. It's missing the physics effect that we can use to reject these events. So, but our machine learning model actually figured it out. It actually tagged all of these events at a very low drift time. That means they are very nearby to the point contact, and is using this as a factor to reject these kind of events, right? So we can actually learn from our machine learning model to understand how to better reject the background in our detector. So that is all I want to tell you. Is a lot of information, but again, I'm not expecting you to understand everything in the first go. So all the slides are going to be posted. So try to use this as a cookbook. So if there is one problem you want to solve in nuclear physics, try to look at this slide and try to do a little bit more research yourself to kind of develop your own machine learning project. So let me try to just very quickly go through all the dots I have connected. So the first I discussed how to analyze high level data. I said you can do feature engineering and use the BDT or SVM to directly analyze those higher level data. So the second is, what if your data is of high dimensional, is more complicated than this kind of time series data? So in this case, first, it depends on how you pre-process your data into different kind of input formats. And also convolutional neural network is in general sense a good model you can use to analyze your data. And lastly, you can perform what we call the geometric deep learning to gain further additional performance from your machine learning model. And the third, I discussed about event simulation using a generative model, mostly variational autoencoder and generative adversarial network. And then I talk about what if your simulated events and the actual data are different from each other? So in this, you can do two things. One thing is to do an unpaired translation to make your simulation looks indistinguishable from the actual data, or you can perform domain adaptation within the transfer learning domain to make sure your model generalizes well between simulated and actual detected data. And then I discussed, can you directly train on real detector data to discover some of the new physics? And to do this, I say you can do this on supervised representation learning, which can actually let the event reveal the physics by its own without having to have some external label. Lastly, I discussed if your collaborator is not happy about the machine learning model you build, what should you do? So first, you should perform some uncertainty quantification of your model, and then you should try to conduct some interpretability study to understand what's the mechanism behind the machine learning model that drives it to make its decision. So lastly, I want to put the same slide I put on the first lecture here. And again, all the lecture materials are going to be posted in this Google Drive link. So please check it out. And if you have any question, I'm happy to take them. Yeah. Okay, any questions? So everyone understand everything I said?
Great, now you can pull out all the exercises.
Well, thank you again, Obo, for joining us for this school. It's been great, and I'm sure there will be lots of people looking back at the material that we made available.
Yeah. Please, or if you have questions about any part of this, just send me an email. I'm happy to answer additional questions. Yeah.
Great. Thanks, Obo.